Hey there, folks. Today we are talking about partition chromatography. Uh, and this is basically kind of the realm of chromatography that is most analogous to liquid extractions, which means it's the kind of the area of chromatography we have spent the overwhelming majority of the semester so far talking about. So that's good. It means that we're all kind of primed to think about this stuff. We've heard about this concept of partition chromatography before. This is the thing that was invented by Martin and Singe, and this was in 1941. So if you remember back to that conversation, the concept there was that these guys took silica particles. And of course, these particles were porous, they weren't solid spheres. So these porous silica particles, let's make sure we're labeling this. So that's a silica, yep, particle. And inside these pores, because this thing was kind of saturated in aqueous solution, we have an aqueous solvent. So they're like sponges that have soaked up aqueous solvent. Um, so these are porous particles. And this, by the way, is all review from something we talked about a few weeks ago. They are saturated with water, some aqueous, probably a buffered aqueous solvent. And the trick here, as compared to adsorption chromatography, the thing that made this uh, a better approach than just adsorption on the polar silica surface is that well, two things. It dramatically increased the volume of the stationary phase. So if you fill these particles with solvent, it's essentially just more volume for things to partition into than in adsorption chromatography when stuff just sticks on the surface. And the thing I've been hammering adsorption chromatography for the entire semester, this gives lower K values, right? Lower retention. And that's because the solvation energy of analytes going into aqueous solution is less than the energy involved in strong hydrogen bonding at the surface of the silica particle. Okay, so here's the problem with this. Here's why this didn't kind of persist as the state of modern partition chromatography, the modern liquid-liquid chromatography to this day. It's that these saturated particles, they just weren't particularly compatible with modern HPLC, right? This was not basically if you make these particles much smaller and you start pushing mobile phase through these things at a pretty high volumetric flow rate, the pressures involved and the shear rates. So basically, let's just enumerate this: the pressures and the shear rates, or the shear force, which we talked about earlier in the semester, that's going to be acting on these solutions, is going to just wash that solvent right out of the particle. So this has given rise, or that problem gave rise quite a long time ago now. This isn't modern technology really by any stretch, but it gave rise to a concept that we're going to talk about for a few minutes here called bonded phases, or bonded stationary phases. The concept of a bonded phase for liquid chromatography is that if we have small enough with small pores and with high surface area, we can actually covalently bond to the surface molecules that would otherwise be liquid solvents. And what they will produce is an environment near that surface that is essentially like the solvent itself, like a liquid solvent. So although they'll be covalently bound, they'll be immobilized on the surface. Those monolayers, because the pores are so small, those monolayers will come so close. So let me see if I can get on camera here. So close together that so you can imagine basically imagine my palms being the walls of a pore and my fingers being molecules that are covalently bound to the walls. Well, if the walls of those pores come close enough together, you get an environment that is just like a solvent anyways, even though the molecules are covalently bound in place, right? I don't know if that was a weird demonstration or not, but that's kind of how I like to think about it. Yeah, so the idea here is that we're going to basically covalently bond solvent molecules. Solvent molecules to the particles. Okay, so the truth is there are actually a number of routes to doing this, and that's because there are a number of different materials that we can make these particles out of. So silica is what I'm going to show you because I think it is by far still the most common material. We've talked about in other modes of chromatography, we've talked about some of the downsides of silica, right? It's not pH stable. It'll start to dissolve at high pHs. So there are polymeric materials that apply here. There's also metallic, so zirconium particles are also really common. I'm going to show you just the chemistry for silica-based phases because, like I said, I think they're by far the most common. So let's take a look at that. So we've talked before, let's get stuff out of the way here. We have talked before about what the surface chemistry of these particles look like. So here is a solid silica particle. So it's a lot of silicon, and hanging at the surface are these silanols, right? These OH groups. And so if you add here another silicon-based molecule, we're called a chlorosilane. This is a silicon with some R groups, some different organic groups hanging off the edge. A little bit later, we'll see why these are R prime, but this one's R. That's going to take a little while to develop. But imagine that one of these substitutions is a chloride. So it turns out that chloride's a pretty decent leaving group here. I'm not pretending like I know reaction chemistry. I really don't. But I do know that in this case, that chloride will leave happily. And so what we'll end up with is our surface. There's the O. We're going to get that silicon with its R groups, its respective R groups. And that H is going to leave, that chloride's going to leave, and we're going to get HCl as a byproduct. Okay, we call this this here, remember this is going to be Si over here. So SiO, we call that a siloxane bond. So siloxane or siloxane bond formed right there. The benefits to forming our bonded phases like this, the first is that this is pretty simple reaction chemistry. So as I mentioned, I am not a synthetic chemist by any stretch of the imagination. If you guys have been listening this semester, you know that to be true. But even I can do these reactions. These are essentially mix and weight aqueous reactions as long as your pH is in kind of the 2 to 7 range. These things will just drive spontaneously. It's pretty straightforward. One of the tricks here that I'll tell you about is these chlorosilanes really don't like water. If you start getting water, basically rather than this silicon substituting onto this silanol, you'll basically get aggregation of these things. Two of these chlorosilanes will bond together to form like a dimer, and then it'll run away as these kind of aggregate products that crash out of solution. Another thing to keep in mind here is that siloxane bond is it's going to be stable in the pH range from these aren't hard and fast rules, but basically all the way down to 2 up to at least 8. I use materials like this pushing pH 9, and I don't think that it's hugely problematic. So if this is how we're going to form, basically what happens is we are forming a stationary phase, and in this case, well, if this is a nonpolar, it's basically an organic, is the equivalent of an organic phase in a liquid-liquid extraction that is immobilized via this siloxane bond to the silica particle. So things are going to dissolve in basically whatever functionality is here as group R. And so the first question maybe we should ask is how much organic solvent, or how much whatever solvent this is, how much of this solvent do we get? So let's think about that for a second. I can tell you it's a fairly straightforward matter of kind of surface characterization to get to an understanding that most base silica materials are going to have something on the order of like 8 micromoles. 8 micromoles of these silanols per square meter of surface area. And it turns out when you have porous particles, a square meter of surface area actually adds up pretty quick. I actually don't have any numbers on me here, but I can tell you that a column is going to have quite a bit more than a meter of surface area. So you get 8 micromoles of these silanols, but the question is not the silanols, right? Because that's not doing the chemistry. The question is how much of this solvent do you get? And so I'll tell you that it is pretty common to say something like on the order of 2 to 4 micromoles are derivatized by this reaction. And so if you want to think about that in terms of yield, obviously that's easy math, right? That's 25 to 50% yield when you do this with particles like this. So the thing to keep in mind, and this is going to come back to us a few times in this discussion today, is that we're going to have, although we're going to have a lot of this functionality on these surfaces, we're also going to have at least half, maybe more, of these silanols still hanging out. That's going to have a consequence we'll talk about a little bit later. Okay, something I'll foreshadow here is that this percent derivatized is influenced, I guess is the word I'll use, influenced by the identity of that R prime group. Okay, so so basically these side groups here, we'll see, oh, sorry, off camera a little bit there. These side groups here, we'll see a little bit later how sterics can influence the ability to functionalize more or less, or to access more or less of these hydroxyls. The reason this matters, the reason this yield thing matters, is because more unreacted SiOH, it leaves more opportunities for adsorption, right? Which is the thing that we're actually trying to avoid here. We would much rather control the nature of the interaction in the stationary phase by controlling this chemistry than be at the mercy of these high energy interactions with these OHs. Okay, so that's kind of the concept of what a bonded phase is. Let's talk about how these bonded phases are used. And there are basically three common modes of partition chromatography that use these bonded phases to kind of do their chemistry. So we'll define these, and then we're gonna make separate breakout videos here for each one of these. So the first is what we'll call normal phase, LC, or NPLC, normal phase liquid chromatography. The biggie, the one that is so ubiquitous that when people say HPLC, sometimes this is all they mean, is reversed phase, LC. So I've mentioned, and a couple people in class seemed to understand this concept, and a couple thought it was weird. But I've mentioned people talking about how HPLC is a separation based on solubility. When people teach it that way, if you've heard that from your undergrad, it's because they were predominantly talking about this reverse phase methodology. And we'll see, hopefully if I do my job well, we will see why they would be predominantly talking about this. It's because it's by far the most common methodology. And then the last one is kind of a relatively new technique, certainly relative to these things. It's super new, right? It's kind of a last 20 years kind of thing. And it's called hydrophilic interaction, LC, or call this HILIC, very common. Okay, so these three modes are basically, they're all going to rely on that bonded phase concept that I just mentioned. I realize my L's look like C's, right? So this is HILIC. There we go. So these all rely on that bonded phase, stationary phase concept. The way that they differ, so these all differ by the composition of the stationary phase. In other words, what are those R groups that we're clicking onto the surface of the stationary phase particles? They differ by what makes a mobile phase strong versus weak. We've talked about this concept before when we talk about gradient elution, right? We go from weak mobile phases to strong mobile phases. And they differ in what is the retention order. If you have a selection of analytes, when do you expect them relative to each other to come off the column, right? What is their retention order? Okay, so this is kind of the introduction to partition chromatography and bonded phases. We are going to move on now to do a couple of breakout videos on each of these specifically.